So it's just this, this vector with each of the components raised to this power. This is useful for what I'll do in a minute, which is kind of discuss Taylor series. We have this notation, which I will just sort of remind everyone. Hopefully everyone's seen this. Just to represent the derivative in one direction with respect to one of our independent variables. So kind of combining these ideas, what we do is we talk about the derivative of this f and this is equal to each of these derivatives with respect, that's one, an alpha I derivative of each of the I independent components, which we can write just as this. We define the order of this alpha to be the sum of each component. Since these are all positive integers, we don't worry about sign or anything like that. So does this kind of make sense? Is this confusing to anyone in terms of this notation? Okay, so again, this is used quite a lot, and it allows us to do some fairly powerful things. One of the things it allows us to do is, we won't do it here, and I'm not sure it's done in the Taylor book, but I have seen PDE papers where they discuss weak derivatives or rational value derivatives. So if we kind of loosen that notion that these alpha I have to be positive integers, we can say, okay, alpha I have to be positive rational numbers, and then we can discuss rational derivatives. I'm not going to go any further in this, I'm just saying that this notation perfectly expresses that concept. So it's another use of it. What we will discuss is how to write something like Taylor's theorem given this notation. So first off, does anyone want an example of this multi-index, or is it very clear what I mean? So I'll take that to mean that it's very clear and no one has any questions about it.
No, it is, yes.
Okay. So we'll talk about Taylor's theorem. This is, of course, the multivariable Taylor's theorem. We defined f as we have before, a map from an open subset of Rn to Rn. And we can just write down in this multi-index notation something like this. We take this alpha derivative of x, we evaluate it at 0. This is kind of the, I think it's called the Maclaurin series, where we take the Taylor series around to 0. We can change this to be any point in Rn, as we normally would. I'll just write it down this way, because this is what Taylor has. And then here's your error term. I'm not going to discuss that, but it's the same error term. So what this means is sum over all possible permutations or combinations of multi-indices.
You need to explain what alpha factorial is.
Right, and I need to define it, you're right. So let me just use his definition. Right, it's the factorial of each of the components of this alpha. So we take each of the components of this and we have the factorial of this. So k is whatever, however far out we take the Taylor series. If k was 2, then this is kind of that quadratic approximation of a function. But since this is in multiple dimensions, sort of in where it's mapping to and where it's mapping from, we just have to be careful that x is a vector here. And each of these alphas can represent in this notation, again, something like this. If we had something like this in R3, my example would be this alpha would represent 2 objects, 2 derivatives in the x1 component, 0 in the x2 component, and 1 in the x3. So it's all possible values of this, where the length or the magnitude of this multi-index is probably less than or equal to k. I think is the correct notation.
Do those x's include things that are products like, like xy or
Yes.
xy squared? Okay.
Right, so it's exactly what I wrote for a polynomial here. My notation is right here. It can be where these alpha 1s or these alpha 2s, are all different. Right?
Well, yeah, just my question was whether it had, something like x1 times x2 in there, or whether it was all like x1 to a power and x5 to
Yeah,
another power.
That's not quite right.
So saying something like,
Like if we're taking a Taylor series in x, y, z,
Right,
I mean,
right,
it
we
mixed
have-
terms that are multiplied
Yeah,
by
we have
xy,
mixed
or is
terms.
it?
I believe this takes the case of mixed terms. Let me think about that.
It doesn't look quite like the notation, that's what I was asking, but.
Right, I'm getting this notation from him.
So what is F? It maps from Rn to Rm.
Right,
Well, but then the right-hand side should be
a vector in Rn.
vector. So F is a vector. X to the alpha should be the product of all x1 to the alpha 1, x2.
I see.
It should not be a vector because F is already a vector in Rm.
Okay, so maybe this notation here is wrong.
It's like the same as the derivative. It should be the product
Products.
of all of them.
Well, if this was the same, then this is wrong, like you're saying. I think that's right, maybe I misread it.
X1 to alpha 1 times,
Something like that.
yeah.
Okay, yeah, that makes more sense. So then each of these elements in Rm can be products, and they will be mixed products of these vectors, which are the
So
components of
x to
Rm.
the alpha is a scalar, and
Right.
the derivative of f is m vector,
Right.
so that both sides are vectors of the same dimension.
Right.
So when you talk about zero that way, does it mean the whole thing? Same
Applying to the
dimension?
zero vector in Rn.
Okay,
Does that make sense?
yes.
So f, the derivative of f is that Jacobian, which is a matrix. But if we apply it to the zero vector in Rn, we get some vector in Rn. And because it's not linear, we can't just call this, of course this would all be zero if f was a linear map. But it's not, it's a general map. So does this make sense? Are there any other questions on this? Okay. So the last thing, again, what I mentioned at the beginning, Dr. Overmead, is that I'll talk for a little while, and then we'll spend maybe the last 20 minutes or 10 minutes discussing choices of books and directions for this seminar, because I'm not sure. I talked with a few grad students, and people have different ideas and different opinions, and there's people here I haven't talked to yet. So the next thing I'm going to discuss briefly is kind of a fundamental local existence theorem for a system of ODEs. So again, since these are ordinary differential equations, we specialize our f by saying that f is a scalar valued map. So m in this case is 1. And what we are talking about, no, I'm sorry. Let me define it the way he does.
If you talk about ODE,
Right.
n is 1, so it's
Right, that's what I meant.
functions of single variable.
Right, so f takes it takes an interval, which is a subset of R. This is kind of our time component, cross our vector space, which is Rn, and then maps this to. Sorry, I'm writing this very badly. It maps